record button. Okay, so like I said, today we're going to be starting chapter 8. And in this chapter, basically what we're going to be doing is learning how to do integrals. That's something that you've of course been practicing since Cal 1, Calculus 1. But what we're going to do now, starting in section or chapter 8, is to put together a lot of the ideas that you've learned over the course of Calculus 1 and Calculus 2 in order to start doing harder and harder problems. Okay, so let's just look at this explanation a little bit. There's a table in the section in your textbook, table 8.1, that has a list of most of the integrals that you've learned how to do since you started your calculus, since you started learning calculus. And let me just switch over to my tab where I have that open so that we can take a look at it. So here's the HTML version of your textbook, and table 8.1 contains most of the basic integration formulas. So you'll see up top how to integrate a constant, and then the power rule. And then starting here, we start to see some rules that we learned in the last chapter. So for the natural logarithm, for the exponential function, for exponential functions with different bases. Then you have lots of trig integrals. These you should have learned number 6 through number 11 are integrals that you learned in Calculus 1. And then numbers 12 through 15 are the kinds of integrals that we did in the section over the natural logarithm. And then we have some integrals with hyperbolic functions. These are the two basic ones that they've included here in the table. And then integrals for inverse trig functions, as well as inverse hyperbolic functions. Okay. So this table of 22 integrals it contains things that you should be familiar with. If you don't quite have it memorized at the moment, that's fine, but you will want to have most of these integrals memorized so that you can do problems on an exam or your homework, etc., quickly. Because, well, this is what we've learned so far in calculus. And let's stop the share screen. So the table, like I said, has all of the integral formulas that you should know or at least be able to use. You've also had lots of other math classes where you've learned how to do problems, solve problems, and we're going to have to remember lots of those other techniques other than the integral formulas, like trig formulas. We'll have to know lots of these. So one of the simplest formulas is this one, which is a version of the Pythagorean theorem, but there's a lot more like this one, like the double angle formulas and angle sum formulas. We'll also need to know algebraic techniques. This is the other big category. These are the kinds of things that you would have learned in your high school math classes, or maybe college algebra, if you took that at the university level. These are things like completing the square, which I know we've done a little bit with in examples. There are a few other things. Multiplying by conjugates, so I'll just write down conjugates. This was a technique that you might have learned in algebra to get square roots out of denominators, that sort of thing. And surprisingly enough, we'll also need to know long division in order to do some of these problems. And this isn't a complete list, of course. You know lots more about math than what I wrote down just there. But our general goal in this chapter is to put together some of these techniques in order to solve more challenging problems than we've been able to do so far. Okay. So starting in this section, I'll be asking you to remember things from all of your math classes going all the way back to algebra and geometry. For example, this problem, if we take a look at the table again, we'll see that this particular integral doesn't show up anywhere in our examples, in our integral formulas, but there are a few down here at the bottom that look a little bit similar to what we're looking at, in particular, number 18 here. So we have a square root and then some sort of quadratic underneath the square root. But there's an issue. Our problem doesn't match up with this formula. We can see there's a constant squared, the a squared minus an x squared, which is a function. And in order to get our problem to match up with that formula, we'll have to complete the square on this one. So this is an algebraic technique that you would have learned in Algebra 1 or Algebra 2. So what we're going to do is look at the quadratic underneath the square root, the 10x minus x squared, and then try to complete the square on it. So we have this minus sign on the x squared term that's going to cause us a little bit of trouble when we try to complete the square. So it would be my recommendation to factor out the minus sign so that we actually have a positive coefficient on x squared. So factor out the minus sign from x squared. That means we have to pick up an extra minus sign on the 10, on the 10x, like this. And I know I've talked about completing the square in the past. The idea is that you start with an expression like this, and then you add and subtract b over 2 squared. In order to get a perfect square when you group together the first three terms. So this would factor, and this is a constant that's left over. So in this particular problem, our b is going to be minus 10. And we'll want to work inside of our parentheses since we factored out that minus sign. We'll need to divide minus 10 by 2 to get minus 5, and then square it to get plus 25. And we have to also subtract so that we don't alter the value of the expression. So the first three terms, if you group them together, you should recognize as a perfect square. How does this factor, this first group of terms? Anyone? Anyone want to give that a try?
X plus or minus 5?
It's a perfect square, so they'll be the same.
Oh, negative 5.
Yeah, well, minus 5 would be the solution if you set it equal to 0. But we're just factoring at the moment. So x plus 5 squared. Oh, excuse me. Minus, of course, since there's a minus sign here. And then you want to bring out the minus 25. Okay, but this is kind of messy because we have this minus sign factored out. So let's rewrite this. So we have two minus signs on 25, and then the minus sign goes with the square here. X minus 5 squared. So this here is how we complete the square for what's underneath the square root there. So we'll rewrite our integral with that. Okay, so I included a lot of detail down here. You don't have to write out all of this if you don't want to. You can do some of that in your head. Are there any questions over completing the square? No? Okay. So now that we've rewritten our integral, it looks like it's in the correct form now, and it is, except there's a function here where the x is. So we'll have to do a small u substitution still. So we're combining this, completing the square technique with another calculus technique that you've learned. I guess you would have learned that last semester in Calculus 1, or whenever you did take Calculus 1, if it wasn't last semester. So let's get rid of this again. So we're going to say u is equal to this bit in parentheses, x minus 5. And then du would be the derivative of this, which is just 1 times dx. Okay. And another point to keep in mind, going back to the integral formula, we can see the constant a squared is here underneath the square root. And for us, since we have a 25, our a will be the number 5, of course. So the answer is going to be sine inverse, arc sine, of x over a plus c, but we have a u substitution going on. So we're going to put our u where x is in the formula. So we get a sine inverse of x minus 5 over 5. And then always remember to add your constant when you're doing an indefinite integral. Okay, are there any questions over that problem? Okay, so we're going to do several more examples in this section, and really this section is mostly just a set of examples to show you different ways that you can combine the techniques that you know in order to complete an integral problem. So if you come across a problem on your homework like this one, where you have some kind of quadratic underneath a square root, this technique of completing the square is something that you could use to answer the problem. And we're going to see several other techniques that you can use in the next few examples. Here's example number 2. We can see it involves several trig functions. We have cosine of 3x times cosine of 4x minus sine of 3x times sine of 4x. And that's what we're integrating. Once again, if you go to the table of integral rules, you'll see that this is a little bit more complicated than anything that shows up in the table. So we're going to have to use some technique in order to simplify it. And I alluded to a little bit earlier that one of our techniques is going to be using trigonometric formulas. And there is a formula that applies in this situation. It's this one. It's one of the angle sum formulas. And if you don't remember these formulas, that's fine. But what I would definitely recommend would be to find a list of common trig formulas. I believe there's one in your textbook somewhere near the end. I don't remember exactly which page it's on. But you can find that in your textbook, or you could just, oops, this should be a sign. Or you could just maybe do a Google search or something to find a table that you can keep handy as you're working through homework assignments. Because you'll definitely need more formulas than you probably are used to using at this point. So this is the one that we need, because you can see we have something of this form, cosine of 3x, so a is going to be 3, and cosine of 4x, 4 will be b, and then you can see these match up in the sine term here at the end. So this whole complicated looking expression simplifies down to a single cosine if we remember this formula. So something very complicated becomes something very simple. Let's see. In the way I've written it here, we don't actually need these x's. I should probably just rewrite this. Rewrite it a little cleaner. That's what I get for trying to talk and write at the same time. Okay, so this whole complicated expression simplifies down to just cosine of 3x plus 4x. So it's cosine of 7x dx. Something complicated becomes very simple as long as we remember a little bit of trigonometry. So you might want to think about this as a u substitution, since we do have a constant multiple of x inside of the cosine. So our du will be 7 dx. And this is why we'll pick up an extra 1/7 constant in the front when we integrate, because of course you have to divide through by 7 to move it to the left side here. So we get a 1/7. And then what's the antiderivative of cosine? The standard antiderivative? Anyone?
Sine.
Sine, good. So we need a 1/7 sine of 7x plus c. Okay. So the new thing that we're learning in this section is to take complicated expressions and rewrite them in simpler forms. Okay. And then maybe I'll write what I was saying earlier, my little hint. It's just to have a table of trig formulas handy so that you can look at it when you need to. So like I said, I believe there is one near the back of your textbook, or if you just wanted to find one on a website, that's totally fine too. I'm sure Wikipedia has a page of trig formulas. Okay, I guess before I move on, are there any questions? Okay, so let's take a look at this next one. This one we have actual limits of integration. This is a definite integral. And we're looking at dx over 1 minus cosine x. This is another one that you won't find a formula for in the table until we do some manipulation. And the thing to notice here is the kind of expression. We have a constant minus some other complicated thing. You might remember from algebra a kind of technique. Let's see, just to pick an example. If you saw an expression like this, you would know that in order to get the square root out of the denominator, you would have to multiply by the conjugate. 2 plus the square root of 3 over 2 plus the square root of 3. So the reason why you multiply by the conjugate is that you end up with just the first term squared minus the second term squared. So this is a technique to get rid of the square root because you pick up the squares. And you could FOIL this out if you wanted to double check that this is indeed what it works out to. So it's actually 4 minus 3, or 1. So this simplifies significantly to 2 plus the square root of 3. So the same technique that you learned in algebra to what you say rationalize your denominators, I believe that's what you called it back then, will also come in handy in calculus we can use the same technique, except now instead of square roots, we might have something like a cosine function. Let me just write out a few of those words. We use the conjugate to what's called rationalize the denominator. So you probably wondered way back in your algebra classes why you always had to do this, why you really needed to get rid of square roots from the denominator. And I think the best explanation for why you need to practice that skill is that it comes in handy when you have harder problems, like this one. The same technique. Okay. So we copy down our limits of integration, and then our denominator, since we're multiplying by the conjugate, we'll get a 1 squared minus cosine squared. So that's just a 1 minus cosine squared x. And you can FOIL this out if you want. If you want to double check me. Okay. So now we have an expression like this one, which seems like maybe it's more complicated than what we started with, but there is a handy trig formula that will help us simplify it. The trig formula that I pointed out on the first page, this one. So this could be rearranged if we move the cosine squared to the right to get a 1 minus cosine squared and then sine squared on the left. Let me write that. Sine squared of x is equal to 1 minus cosine squared. So this denominator, which seems more complicated than what we start with, actually simplifies. Any questions so far before we finish off the integral? No? Okay. So now we have two terms in the numerator divided by our denominator. We should split this up into two separate terms. So 1 over sine squared and cosine over sine squared. And unfortunately, I'm out of paper, or I'm out of room on my paper, so we'll have to go to the back side of the sheet. Okay, so this is what we were looking at. We had an integral this integral, and we want to separate it out into a 1 over sine squared plus cosine over sine squared. And the reason why we want to do this is that these expressions match up with other trig functions. We can rewrite them. What is 1 over sine squared in terms of other trig functions?
Is it cosecant squared?
Yeah, exactly. So we're actually looking at a cosecant squared. And then cosine over sine. What function is that? What's cosine over sine?
Is it cotangent?
Cotangent, right. So we're looking at a cotangent, and then we have an extra 1 over sine. So we actually have an extra cosecant. And then we have our cotangent. Good. And these expressions, if we go back to our table, and I can pull it up for us, we can find. So here's cosecant squared, bullet point number 9. And number 11 has the cosecant times cotangent. So after all that hard work of trying to simplify and rearrange, we finally come to an answer, something that we can actually integrate. So we get a minus cotangent, and then we get a minus cosecant. And then our limits of integration still need to be plugged in. So at the very end, even after we've already done lots of complicated things involving algebra and trigonometry and calculus, we still have to remember the unit circle. We have to plug in some values. Start with pi over 2. And then subtract and plug in pi over 4. Okay, so I don't want to spend too much time working with you on the unit circle. When you look up the trig formulas, you should also look up the unit circle and review it, or at least have it handy so that you can look at it. What we'll get here is a minus 0, minus 1, and then our minus sign, and inside the parentheses, we'll pick up a minus 1 and a minus square root 2 from these two. So definitely look those values up if you're not familiar with them. But here, the minus 1 will cancel off with this negative 1 or plus 1. The only thing left will be the minus the square root of 2. So that's our answer. So that's for the whole step here. You'll have to remember the unit circle. Any questions over this problem? No? Okay. So just to remind you, we started here, number 3. We did several steps on this page, and then we continued working on the back. So something that you'll notice about these problems that you're going to have to do starting in chapter 8 is that they're starting to get much longer than they were. You have to do quite a few things to your problem in order to get to the final answer. So you're going to have to, what expression do I want? You're going to need a little bit of tenacity, I think. in order to keep on going until you finally get to the answer, even if it does take, 5 or 10 minutes of hard work. So let's do this one, number 4. So this is a rational function. You have a polynomial on top of your fraction and another polynomial on the bottom. But something that you should notice about this particular function is that the power of x in the numerator is larger than the power of x in the denominator. So this is something like an improper fraction, where the top is larger than the bottom. And something that you learned way back in your algebra classes was how to rewrite, or maybe even going back to elementary school before you got to algebra, you learned how to rewrite improper fractions as something like a whole number plus a proper fraction. And that's what we're going to do here, except now we have polynomials instead of, just numbers. So we have to remember how to do polynomial long division. And hopefully an example will jog your memory on how to do that. So we're going to take the top and actually divide it by the denominator. So set up your long division problem like you did back in grade school. And what we have to do is figure out what to multiply the first term by in order to cancel off the first term of the thing that we're dividing, the 3x squared minus 7x. So what do you have to multiply by in order to cancel that off when you subtract? X, good. Yeah, so in order to keep things organized, you want to find your corresponding x term underneath the division symbol and write what you're doing up there. So multiply by x, you get a 3x squared plus 2x. And then you subtract, just like you do, or just like you did when you learned long division in elementary school. So the first terms cancel, and minus 7x minus 2x gives us a minus 9x. So what do we have to multiply 3x by in order to cancel off the minus 9x? Anyone? Minus 3, good. Okay, so multiply through by minus 3, you get a minus 9, minus 9x, minus 6. And subtract. You'll have to think about distributing through the minus sign as you subtract. The first terms will cancel, of course, and you'll be left with minus negative 6 or positive 6. Okay, so this is the remainder here. And now we know how to rewrite this expression. We know it's going to be x minus 3 plus the remainder over 3x plus 2. So we go back to the integral. We write what do we call this? The dividend, I believe. X minus 3, and then the remainder, 6, over the denominator, 3x plus 2. Okay. So now that we've done long division, we end up with something that we can actually integrate. Because we know how to integrate x, that'll be a 1/2 x squared. You know how to integrate a constant, like minus 3. That'll give us a minus 3x. And this one, we'll have to do a minor little u substitution for. So u is equal to the denominator, 3x plus 2. du is equal to 3 dx. So we can rewrite this as 2 over u. So I've pulled a 3 out of the 6, and a 2 is left over. And this gives us a natural logarithm. So it's 2 times the natural logarithm of u, with an absolute value symbol. So that takes care of all 3 terms there. We just need to add a constant on the end. Okay, any questions so far? No questions? Okay, so there's 5 minutes left in class. So I think this is probably a good stopping point so that we don't run over. I do have a couple more examples in this section, but these tend to take longer than a couple minutes apiece. So we'll save those for Friday morning. If you have any homework questions or anything like that that you've thought of, now would be a good time to ask those. Otherwise, I will see you guys Friday, and we'll stop a little bit early.